So separable equations. A first order differential equation that has the form dy dx equals g of x times h of y is said to be separable. Or to have separable variables. So now we're going to take a look at several equations and determine whether they're separable or not. So, in the first equation, x prime equals x times t plus 2x. So if we look at this, we can rewrite this as dx dt equals x times t plus 2. Here we can write g of x to be x, and then h of t to be t plus 2. Notice that we've now written this in the form of dx dt equals a function of x times a function of t. Therefore, this is separable. Let's now look at x prime equals x plus cosine of t. Now, this can be written dx dt equals, and there's nothing we can do on the right hand side, so x plus cosine of t. Notice there's no way to write this as a function of x times a function of t. So this is not separable. Now let's look at the function, or I'm sorry, the equation. X prime equals x times t squared plus t squared minus t times x minus t. Now this, we can write dx dt equals, we can factor out an x, so we can factor out t squared from the first terms, so t squared times x plus 1. We can factor out a negative t from the second two terms, and we're left again with x plus 1. And so we can now factor out an x plus 1 and be left with t squared minus t. If we write this as g of x, we can write this as h of t, and we now have a function of x times a function of t, and hence this is separable. Finally, let's consider the equation x prime equals x squared plus x plus 3. Now this can be written in the form dx dt equals x squared plus x plus 3. Now it may not seem like we have a function of t. However, remember, if we multiply anything by 1, it doesn't change. So now we can say this is a function of x, and 1 is our function of t. Therefore, this equation is also separable. Let's now look at how we would solve a separable equation. So first we want to make sure that the separable equation is written in the form of dy dx equals some function of x times some function of y. We can now divide both sides by h of y, and we'll get a function of y times dy dx is equal to our function g of x. Here note that we're replacing 1 over h of y with p of y. Now, let y equal phi of x be a solution. Then what we must have is p of phi of x times phi prime of x has to equal g of x. So, the integral p of phi of x times phi prime of x dx would have to be the integral of g of x dx. Now, we said that y is phi of x. Which means that dy would be phi prime of x dx. So we can write the above now as the integral of p of y dy is equal to the integral of g of x dx. And so we can write this as h of y is equal to g of x plus some constant, where h of y is an antiderivative of p of y, which remember we said was 1 over h of y, and g of x is an antiderivative of g of x. Now there should be some care when using separation of variables, since the variable divisors could be 0 at a point. Specifically, if r is a 0 of the function h of y, then if we substitute y equals r into our differential equation, both sides are 0. This means that y equals r is a solution. However, dy over h of y becomes undefined. At y equals r. And so we may not actually get y equals r as a solution when we do the above method. So it's important that whenever you do separation of variables, you check when your h of y is 0 and make sure that you include those as a solution. We're now going to look at 3 examples of separable equations, and we're going to solve them. The last one we look at will be an initial value problem. So let's start with the equation. X prime of t is equal to t times x plus 1. So this is of the form dx dt equals t times x plus 1. This is separable. So we can write this as dx over x plus 1 is equal to t times dt. Now I'm going to make a note here. If x is negative 1, then x plus 1 is 0. So we want to make sure that we can get x equals negative 1 from our solution. What we can now do is integrate both sides. So we get the integral dx over x plus 1 is equal to the integral of t dt. And you should remember from calculus that the integral of dx over x plus 1 will be the natural log of the absolute value of x plus 1. And the antiderivative of t is t squared over 2. And now let's add in a constant of integration. We now need to solve this for x. So to undo a logarithm, we take both sides as the exponent of base e. So we're left with the absolute value of x plus 1 is equal to e to the t squared over 2 plus our arbitrary constant, which is e to the t squared over 2 times e to this constant. Absolute value, of course, means plus or minus. So we have x plus 1 is equal to plus or minus e to the t squared over 2 times e to our constant. But e to a constant, so this value right here, is still constant. So let's replace it with c1. And we can write plus or minus c1 times e to the t squared over 2. So we get as a solution x of t is equal to plus or minus c1 times e to the t squared over 2 minus 1. Now, can we get x equals negative 1 out of this solution? We can. If c1 is 0, then we get x equals negative 1. Now, this plus or minus is also a constant. So we can write this even simpler as simply x of t is equal to c1 e to the t squared over 2. And we have our solution. We now look at the equation dy dx is equal to y squared minus 4. So we can rewrite this as dy over y squared minus 4 is equal to dx. Now, let's take note that the zeros of y squared minus 4 are plus minus 2. We now have the integral dy over y squared minus 4 is equal to the integral of dx. Now, this would require partial fractions, which was studied in Calculus 2. We're simply going to use a calculator because I'm going to assume that you know all of the techniques of Calc 2. To determine the antiderivative of dy over y squared minus 4 using a calculator, we see we have our TI Inspire CX2 CAS up here. So we're going to do menu. I'm going to come up here to number 4, which is calculus. 3, which is the integral. Click it. Now, since this is a definite integral, we're going to leave these two blank. So I'm just going to hit tab twice. Brings me into my main body. So now we type in the function 1 divided by y squared minus 4. I need to move this over because I need to put this denominator in parentheses. Tab. With respect to a variable, well, this is with respect to y. Now we just hit enter. And we see we get negative natural log absolute value of y plus 2 over absolute value of y minus 2, all divided by 4. So this is our antiderivative. So this will now give us negative log of the absolute value of y plus 2 over y minus 2 all over 4 is equal to x plus some constant. Now we can rewrite the left-hand side using properties of logarithms as a quarter times the log of the absolute value of y minus 2 over y plus 2. Of course, equals x plus c. Our goal now is to solve for y. So to do this, we first have to multiply both sides by 4. So we have the log of the absolute value of y minus 2 over y plus 2 is equal to 4 times x plus a constant, which of course is 4x plus 4 times a constant. We can write 4 times a constant as just a constant, so I'm going to keep it just as plus c. Again, to undo a log, we take that as the exponent, base e, and so we're going to have y minus 2 over y plus 2 is equal to e to the 4x plus c, which is of course e to the 4x times e to the c. And e to the c is still a constant, so I'm going to write it as c e to the 4x. I'm sorry, this should be the absolute value. This means that y minus 2 over y plus 2 is equal to plus or minus this constant, e to the 4x. And of course, plus or minus a constant is still a constant, so constant e to the 4x. What we have to do now is multiply both sides by y plus 2. So y minus 2 is equal to y plus 2 times the constant e to the 4x, which is, of course, cy e to the 4x plus 2c e to the 4x. We want to move all of our y's together. So I'm going to move all my y terms over to the left-hand side and move all my other terms to the right-hand side. This will now give us y minus cy e to the 4x is equal to 2c e to the 4x plus 2. And of course, this 2c is a constant, so I can just write it as c e to the 4x plus 2. Now if I factor out a y, we get y times 1 minus c e to the 4x is equal to c e to the 4x plus 2. I can now divide by that 1 minus c e to the 4x to get y is equal to c e to the 4x plus 2 all over 1 minus c e to the 4x. Can we get the zeros out of this? Well, if we set c equal to 0, we get y equals 2. However, there is no way to get negative 2. And so, we have to write our solution as y of x is equal to c e to the 4x plus 2 over 1 minus c e to the 4x, and also y of x is equal to negative 2. And so these are our two solutions. Finally, let's consider the initial value problem. E to the 2y minus y cosine of x dy dx equals e to the y sine of 2x with the condition y of 0 is equal to 0. Now remember, to solve an initial value problem, we must first find the general solution. Then we can use the condition to determine the constant. So we're going to write this equation in separable form first. So e to the 2y minus y, all divided by e to the y dy equals sine of 2x over cosine of x dx. We will now simplify both sides. To simplify the left, we're just going to divide each term in the numerator by e to the y. To simplify the right-hand side, we make use of the double angle formula. Sine of 2x is equal to 2 sine x cosine x. So the right-hand side will simplify to 2 sine of x dx. We can now integrate both sides. So we go again to Menu, Calculus, Integral. Again, hit Tab twice. We're going to leave those blank. And we type in in parentheses, e to the y minus y times e to the negative y with respect to y, we get y plus 1 times e to the negative y plus e to the y. So this becomes y plus 1 e to the minus y plus e to the y is equal to negative 2 cosine x plus a constant. If we now apply our initial condition, which says whenever x is 0, y is 0, we'll get 0 plus 1 times e to the 0 plus e to the 0 is equal to negative 2 cosine of 0 plus our constant. Since e to the 0 is 1, the left-hand side is 2. Cosine of 0 is 1, so the left-hand side becomes negative 2 plus c. So this would mean that c is equal to 4. And so our solution is y plus 1 e to the negative y plus e to the y is equal to 4 minus 2 cosine of x. Since we cannot explicitly solve for y, we leave our solution in this form, which of course, remember, is called an implicit form. That concludes our lesson on separable variables. I hope you learned something, and we will see you in the next one.